Right, evening everyone. So yeah, this is a new format that we're trying tonight, where we're going to try and answer some of your questions. We'll start off with introductions. So I'm Thomas. I am a PhD student here at Cardiff, and my research focuses on the gas around galaxies, something called the circumgalactic medium. This is what keeps star formation in galaxies across every massive galaxy you can think of, and I study that with simulations. I don't use telescopes. We code all our physics into simulations and let that run to try and create realistic galaxies.
Hello, I am Aparna. I asked ChatGPT what the best way to present my research is, and it said call yourself a cosmic historian, so that's what I am. But I study light that's from the beginning of the universe, and I look at galaxies that are way far back in time. But I try to make connections between how the galaxies looked back then, why they look like that, with comparing them to galaxies that we have in our cosmic backyard, so to speak. Yeah. Should be any questions about observations?
Hello everyone, I'm Hugh, I'm a PhD student at Cardiff. I look at how gas moves in molecular clouds, in the Milky Way specifically. All of my clouds are full of carbon monoxide, and so would kill us all if they were here. So I'm glad they're not. And I'm hoping to see how the processes inside these clouds are going to affect star formation. So if we guys have any questions about that.
Okay, so before we get to the first question, you guys submitted, I'm going to run through the ones that you printed down on paper. If we have time, I'll take any more questions that you think of as you go. If there are any sort of follow-ups to anything we're talking about, stick your hand up and we'll go to you. The other thing to mention is we had planned to have a couple of extra people on the panel tonight, covering things like exoplanets, supernova. So if you have questions about those, I don't see any in here, but if there are, we'll do our best to answer them, but we may have to get a better answer for you in our next event in February. But I think we'll start with a question here for Aparna. Is there anything further than our galaxy?
Short answer is yes. The long answer is there's so many, we will lose track of numbers at some point, counting all of them. I'm not sure what this was referring to in specific objects, but if you were to hold your arm out and just, look at the patch of sky that your palm covers on the sky, there's more galaxies in that small speck of area than there are grains of sand on planet Earth. We can keep looking at these places and like small patches of sky forever, and we will still keep finding new things. That's just how vast space is.
Really, like two immediate follow-ups. So obviously there's loads of stuff beyond our galaxy. What is the furthest object that we've spotted?
So the furthest object that we can see, object is a bit loosely defined here, but it's the cosmic microwave background. This is the leftover radiation from when the Big Bang happened. It is physically impossible to see anything before this particular time in the universe's evolving history. Because the line has taken too long to travel to us, and it's just like we've missed the bus in terms of like seeing what lies behind it. But for now, that's like the Raman radiation and the earliest object, so to speak, that we can trace.
And then another one before I move on and like you answer something is given this relates directly to your research, how does gravitational lensing help us?
Right, so
Maybe we can start with what it is first.
yeah, gravitational lensing is really cool. So if you have a paper with some really, really tiny text, you would pick up a magnifying glass to read it better. Gravitational lensing is basically a magnifying glass for the universe. But this is not something that we've invented, the universe gives it to us. It's this amazing phenomenon where you have a really massive object that bends the light around it. So say you had a massive galaxy where Thomas is, and then there is an even massive galaxy where Hugh is, and you are that way. You are obviously closer to Hugh, and you cannot see through Hugh that there is something where Thomas is standing. However, if you just look at the light that's coming from the galaxy where Thomas is at, it will get bent around the mass distribution that is Hugh. So you will sort of see an image of what the galaxy looks like. You will have to reconstruct it, that's a whole other pain in the backside. But you will see what we call as lensed arcs. So sometimes when you look at these pictures that come out from Hubble or like James Webb Space Telescope, you will see images with arcs. That's what those arcs are. It's basically something in the middle that's bending the light from the original source to the point where it's just arcing. And the best way I can tell you to experiment this for yourself is go home, have a piece of paper that has some text on it, and run a wine glass over it. You know, the stem, like the ones with a flat base. You can see that as it gets closer to the stem, the alphabets will start arcing. That's exactly what gram lensing is. It's fantastic, and we can observe objects that are pretty much forming at the beginning of time because of this phenomenon, because otherwise our technological capabilities right now do not let us see that far. But yeah, this is like nature just built this and it just went use this. You know, if you are that interested in astronomy, look at this. Yeah, that's basically it in a nutshell.
Yeah, I think we got stuff like 200 million years after the Big Bang because of this.
Yeah.
I think there's some of the early JWST images, so there's like a galaxy that's being gravitationally lensed by something in front of it that looks like a question mark because of just how the light is moved.
Yeah.
So I'm gonna, before I ask something maybe we can all try and answer, I'm gonna come to this one. What is the most interesting application of AI, artificial intelligence, that's happening in astronomy? And I think I'm gonna start with that because there's a few things I can basically say here. So first off is like artificial intelligence as like the media talks about it. Sort of generative AI, ChatGPT type AI. That's, I mean, it's got its place, it's really impressive technology, IP theft notwithstanding. What we do in astronomy falls more under sort of a specific subset of artificial intelligence called machine learning or deep learning, where we'll use these computational algorithms to synthesize huge amounts of data. And there's more ways that I can go into this. There's more ways that we use this than I can go into just now. So the simulations that I work on and the ones like them, there's some of them are absolutely gigantic with thousands and thousands of galaxies in them. And trying to understand like what's affecting these galaxies as a population can be done with sort of standard statistical methods, but running them through these machine learning algorithms is really helpful. Particularly if you've got like thousands of images of different galaxies and you want to say, that one's a spiral, that one's sort of an elliptical, that's something else, maybe that one's got a bar. And I was reading a paper today that's been doing exactly that with both observed and simulated galaxies. But then you've got also so many other applications of it. But what's maybe more interesting is how we actually train those models. There's a whole project called Galaxy Zoo. So we have these survey telescopes that take images of thousands of real galaxies. And for astronomers like us, there's not that many of us in the world. It would take a very long time for us to go through every single image of every single galaxy and say, that's a spiral, that's an elliptical, that's something else. But we need to have all those labels to train an AI model. So what we do is there's a website called Galaxy Zoo, and members of the public, it's a citizen science project, members of the public will basically show image after image after image after image and say, that's a spiral, that's an elliptical, that's two that are merging together, and adds all those labels. So you've got maybe 10 people that have all said, yeah, that's a spiral, then we're pretty confident that's a spiral. And we can use that to then train these AI models to make our lives a lot easier when we're dealing with thousands of objects and we do not have enough time.
I have one thing to add on. So I know a friend who did a PhD project in something called molecular clouds, which he will let you know about later. But basically, these are tiny gas clouds that exist, in every galaxy, but we can only see the ones that are inside the Milky Way because that's close enough. He had to classify by hand 15,000 galaxies. He looked at every single image to put them in a box because he had to train them. Like there was no pre-existing model before AI came in, and he had to do them by eye. So one of his papers is literally him categorizing 15,000 molecular clouds by eye. And then he trained an AI model saying that, okay, I used a model, I trained it, and I verified it by eye. And that was his second paper. So this is how we can stop wasting man hours on just, basically mundane tasks like this. Like we can better use our resources and hours to actually do research instead of looking at pictures, which is also nice. I'm not saying that's bad, but 15,000 of them is probably not good.
Yeah, and actually on that point, if anyone wants to contribute to things like Galaxy Zoo, please do. It is so helpful to people in sort of astronomy research.
You do get a little tutorial. You don't just go in blind. Like it'll tell you what to look for and everything. That's it.
Okay, actually speaking of that, Hugh, do you want to tell us a bit about like molecular clouds? What are they? Why do we care? There's approximately 15,000 of them. So.
Yeah, so a lot of my work is done on the Milky Way, and that's, if you're looking at molecular clouds and you want to see them in any detail, that's really the only place you can look at them. Because extragalactically, they are, you can only just see where the gas is, you can't really resolve any points or objects, unfortunately yet. Molecular clouds are basically the birthplaces of all of the stars that we've ever observed. So they are great ways at looking at how these stars have formed in the past. As you can see, each molecular cloud you look at is at a different stage in its evolution. So some of them might be quite diffuse and it's still, gosh, I should be careful with the words I use. Diffuse meaning sort of that all the gases not very close together. Yeah, I shouldn't move this way from my anyway over here. Yeah, it's not very concentrated. All the gas is quite far apart. You're unlikely to see many of these clouds because a lot of what we look at are the emission from these clouds. It's the light coming from them, and you need a lot of it to really be able to see that. So quite a lot of the clouds I look at are very sparse, but more and more of them are very. There's lots of dense material in the centre, and that would be the place where stars will form eventually. That sort of scale of hundreds of millions of years. None of the stars none of the potential stars in my clouds are going to form in my lifetime, so I'll never see them form.
Yeah. I mean, 100 million of years still feels kind of fast to me in extragalactic astronomy, but yeah.
That's sort of your supermassive stars that we think what I'm talking about.
Yeah, I mean, 100 million of years is like between like outputs from my simulations. we don't deal with normal timescales in astronomy. So we had a few questions about sort of black holes and stuff. I think quite a few people have seen Interstellar. So I don't know if maybe Aparna, you want to try and answer this one? Because none of us have the answer to this one. What do you think is inside a black hole?
Everything and nothing. That's we don't know. It's impossible to actually fall in and come up and let people know what they saw inside. Yeah, for now we just assume everything that goes in stays inside. That's basically it.
Yeah. So the reason for that is like black holes. The reason we call black holes is because there's so much mass concentrated in such a tiny volume that there's a region around where you have to go faster than the speed of light to escape. Which means that the end of Interstellar is nonsense, essentially. But there was another question of could the water planet orbiting the black hole in Interstellar actually exist? And that's a pretty good question, and I don't know how to fully answer it, but I'm going to give you a bit of an attempt. So, I'm going to show you back and say, can planets exist around black holes? And the answer to that is absolutely yes, they can, because a lot of black holes in our universe, not the ones in, let's leave Interstellar to the side just now, but a lot of the black holes in our universe exist in what are called binary systems. So, most of the stars in our galaxy, we will have a companion. So you'll have two stars orbiting each other, or maybe two stars orbiting with another one orbiting around that. And we do know of some planets that orbit in these what we call multiple systems with more than one star. If you've got, say, two stars in a system orbiting each other, and one of them's really big, then eventually it's going to go supernova. And if it's big enough, that supernova will leave behind a black hole. So if you've got a planet orbiting far enough away from that, it should survive. But there's going to end up with water on it, I think, is a big question. To be fair, we don't really know what's on the surface of any empty planet.
The only thing I would say is the physics that went into making Interstellar is actually real. Like the black hole simulation that you see was actually used to publish several papers on black holes because the movie got more funding than science did. There is a joke in there somewhere. But as far as whether the planet actually exists, I think it might be because there is something called a stable orbit around a black hole where things can exist, but they will just be permanently locked to that orbit. If it deviates even a little bit, say an asteroid came at you a little too enthusiastically, you will be knocked out and you will go straight into the black hole, or you will escape the gravity and get kicked out entirely. So it's called, I can't remember what the exact acronym is, but it's called, like, it's the last stable orbit before everything disintegrates into the black hole. And if the planet stays in that orbit, yes, but again, like I said, it's super precarious. If something like the meteorite that wiped out dinosaurs came at it, it probably will get knocked out.
What I will say is the size of the waves on the planet, I mean, maybe not the size of them is correct, but for something so close to a black hole, it would certainly experience tides and therefore waves. And so I would expect probably larger waves than you even see in stellar, but there are definitely waves.
Makes a little sense.
It does, and I think maybe sticking with stuff that kind of captures the media's attention, we had a couple of questions on this. Do you think that we'll find intelligent, in brackets, extraterrestrial life in our lifetime? If so, where is most likely? Let's just start with extraterrestrial life.
So yeah, I'm not going to start with intelligent life because I have no idea about that, but I mean, Sumisaka, one of the academics at Cardiff University, has given many presentations and courses in the past, so I'm sure if you have been here for very long, you definitely know the K218b. It's an exoplanet that's thought to have had detections of, I want to get this right, is it eukaryotic or prokaryotic? I can't remember. One of them is single cell life. I can't remember which one's the correct word. So there are things called biosignatures, which can indicate whether or not life is present on a planet. And one of them is dimethyl sulfate. I'm not a biologist or a chemist, so don't ask me on how that is a biosignature, because I won't be able to tell you. But it is. I take it as gospel. And there have been tentative measurements, detections of dimethyl sulfate, K218b, in the water there, or in the atmosphere there, sorry, not the water. So potentially we have already, but the detections are not significant enough to say so yet. But as to intelligent life, I'm not sure. I'll leave it there.
The one thing I will add though, in these studies we are looking for life as we know it. Life might exist in a different form as well. They might not be carbon-based life forms. So yeah, we would need to be a little bit more open-minded on like what kind of biosignatures we restrict ourselves to. So if we are looking at life that resembles what we have on Earth, then maybe we are narrowing down, what we might detect. So yeah, we just need to see what other forms of life can exist.
Yeah, and just because we don't want you to go with the wrong impression, the K218b thing, let's bring in the sort of, truckload of salt on this. This tends to detect, like dimethyl sulfide. When we say it's a biosignature, these are substances that we think can only be produced by life because of what we know about Earth. So this molecule, dimethyl sulfide, we know it can create in industrial processes, but the only natural way we know how to produce it is with like plankton around ocean vents, so single cell organisms. So that's why we think it's a biosignature. But the same observations that have said we think this is a biosignature and we think that this planet might have like an ocean on it and there could be life within its oceans. The same data has been interpreted by other groups as, no, this thing is like Mustafar from Star Wars, it's a complete like lava planet. So yeah, but the exoplanet modelers are not particularly sure on what this planet is.
It's a hot topic.
Yeah, there's a lot of disagreement about it.
watch this space.
On the topic of intelligent life, I don't know if we'll find it within our lifetimes, but I think it's, like, we talked about the universe being infinite. If it's infinite, then just about anything can exist somewhere, so it probably exists somewhere. Whether we'll ever meet it is another question entirely. What's that one? So we'll bring it back a little bit maybe away from actual astronomy as a science and more the fact that we're all PhD students. We're all here at Cardiff University doing our PhDs. So I'll start off with this question: what is the best part of doing a PhD? That's it you first, or?
He's the more recent PhD student.
Probably for me, everything you're doing is new, and so in the circle that is all knowledge that exists, you are a little pimple on the outside of increasing knowledge, and that's very exciting. So yeah, it's awesome to be part of increasing the knowledge of all humanity. That would be my take on it.
It's really cool. So like the stuff I work on, because it's called high redshift galaxies, it's galaxies that are so far behind in time we thought we would never see them. But looking at those pictures, sometimes even now, I say even now, it's just been like my second year in, it gives me goosebumps because you look at these sources and then you think, light traveled 13 billion years to get to me, and I'm getting to look at it from like all of these different telescopes, and I'm trying to categorize what is essentially a smudge in the sky. Like I'm basically working with 4 pixels of data, and I'm somehow extracting meaningful information out of it. Bonkers. I can't wrap my head around it. So yeah, that's a nice feeling to have on the days I'm doing that.
Yeah, for me, I guess I've always loved learning, and PhD is the best opportunity to do that. But I feel historically observers, but I take special pleasure with the fact I do simulations because these images are great, but our simulations tend to look a little bit better. I'm not dealing with 4 pixels; I'm dealing with like terabytes of simulation data. It was great. Yeah, that's more than that. I'll give you that. And the other thing that I'm spoiled by the data that we get because, like, I know exactly where everything in my simulations are. I can move it around. I can turn it. I can do it. I only want the stuff that's making stars or whatever. I have so much more control over it than I guess observers do. But the best part of PhD is just being able to just spend every day learning about something just for the sake of learning it. I think kind of what you said. So. Next question. What is the scariest fact about space that you know?
I don't think people realize how vast space is. If you knew what spatial scales are, like how far apart objects are from each other, you will realize that most of space is basically empty space. Even though we see so many stars in the sky, I just told you there are like a bazillion galaxies. They are very, very far apart from each other. And we are essentially a floating rock that's very isolated and in a very opportune location in our solar system, because if we were even, where Mars is right now, we would not exist as a species. So I think there are 2 ways to look at it. One, you look at the darkness and the darkness stares back at you, or you just look at it and you're like, damn, that's a lot to explore, and you just keep going. You can either let it consume you or fascinate you. That's how I look at it.
So for me, probably the most terrifying thing is the furthest we can see in terms of distance is not as far as the universe expands, and that's very true. So we will never see. We'll never see the edge of the universe, which is what makes me think that potentially there's intelligent life, but it could be outside of our observable universe, because we have the light from the Big Bang. That's as far back as we can see. It's or as far in terms of distance we can see, but that's not as far as it goes, because say the universe had a point here where the Big Bang happened. You've got stuff moving off this way. If we happen to be this way, we can see as far back as the Big Bang, but the stuff on the other side, that's assuming it's circular, which is also a very big assumption to assume it's spherical or circular at all. That's lost to time. We will never, unless we develop any sort of that sort of picture or any sort of faster than light travel, we will never see that. That's terrifying.
Yeah, I think for me it's just, and you kind of touched on this, just how lucky sort of humanity got to be here on Earth right now, exactly where Earth is. Because I was a galaxy astronomer, but I looked into a bit just like recently on like solar system formation stuff, and there was absolute possibility that one of the gas giants could just wander into the inner solar system and eat us out of existence. There's the possibility the sun could have been a little bit bigger and we would have been fried or turned into Venus, or it could have been too small and we would have been frozen. But everything just kind of worked well enough for Earth to form as it is, for it to be habitable for now. And yeah, now we get to look at space and wonder about being absolutely tiny and insignificant. Speaking of being tiny and insignificant, I'm going to regret this right now. Have you heard about Pluto?
See, I am in favor of Pluto being classified as a planet, but the biggest advocate for Pluto not being a planet is actually not here today. But yeah, I'm sure he will have a few words to say. Pluto should be a planet.
I'm on the opposite side of that. I do not believe Pluto should be a planet. I am very much of the opinion that the new classification of a planet, if I say new, I don't know, like 2006, yeah? Yeah, so not that new. The new classification of a planet is a planet must have cleared its orbit, and Pluto has not done that. But that's one of the classifications. I don't remember the rest.
Under the old classification, how many planets would there be in the solar system?
A lot more.
Yeah, a lot more. But quite a lot of the things we call dwarf planets or moons.
I think both of
Yes,
Ceres and
Ceres
planets.
and Mathematica.
Yeah. And Jupiter will have like 50 new moons.
Yeah.
Because it just simply has a lot of demand.
I do think it's a good classification to say that it must have cleared its orbit. It must be the largest thing in a part of its orbit, and anything else in its orbit has been basically consumed or been knocked away by it. Which could be said for Jupiter, right? and all of the other planets that we consider planets. I think that's a good classification.
Yeah, I mean, it's a pretty good classification. The problem is, like, people tend to think of it as like, oh, it's kind of based on mass, but then there's so many like moons of Jupiter and Saturn that are huge. So there are a few moons that are bigger than Mercury, and the only reason they're not counted as planets is because they are orbiting things like Jupiter and Saturn. I kind of land somewhere between. I do not mind if we reclassify Pluto as a planet, but if we're going to do that, then we kind of have to do the rest of them as well. So, I don't know, more planets would be more fun. Remember there's an April Fool's paper a couple of years ago that was like, yeah, everything is a planet. Planets all the way down, galaxies, stars, and it's just
I
planets.
think it said something like Earth was not a planet but anything else.
Something like that, yeah.
That was hilarious.
Yeah, so I think we probably don't want to spend too much more time on this, but are there any more questions from the floor before we do a wrap up? Yes.
Is there any research on if in like a billion years Pluto has cleared its orbit, like somehow eaten everything in its orbit, could it become a planet?
I don't know if any research particularly on it, but I think it's probably unlikely. Pluto exists in something called the Kuiper Belt. So we have a few different asteroid belts in the solar system. You have the asteroid belt that exists between Mars and Jupiter, big ring of debris. And then beyond Neptune, you have the Kuiper Belt, which is also full of loads of small chunks of ice and rock and such. And Pluto exists within that. So it would have to carve out a hole in the Kuiper Belt. And it's just not very big at all. Chances of it doing it pretty slim.
If some of them came together and then they merged with Pluto.
Possibly, but a billion years might not be enough time. Everything in astronomy is very, very small.
Billion.
Also, I don't think planetary merging is a concept in and of itself, because they just get this, like, it's mutually assured destruction if another object comes on a planet, because you're just breaking apart both things. Like, for example, I think the moon was formed like that, if I might be completely putting this out of the air. But yeah, the moon basically formed because the Earth got hit by a couple of asteroids every now and then, I don't know, a couple of billion years ago. And that's how, yeah, and that's why we have a moon. We also have several other tiny objects that could be classified as a moon floating about, but yeah. Yeah, so I don't think there's a planetary origin in anything that's possible.
Okay. Any other questions? Yes.
So you talked about the joys of doing a PhD and all the things you learn from it, and you're all very young, so it's going to have, 50, 60 years from now, 70 years from now, you look back on your life of astronomy, what would be the thing that you would love to have said that you achieved with that? What discovery or what? You would look back and go, that was really worth it.
I personally, so I, like I said, I work in simulations, and there's this big, one of the big disagreements in simulations of galaxies is, do magnetic fields matter? You get some people that do simulations and say, yes, absolutely, definitely matters, affects how gas moves, affects how galaxies grow and all that sort of thing. I fall in that camp, my simulations show that. There are people that do different simulations, a different physical models, say, nah, it doesn't matter, we can just leave them out, we don't really need them unless you're caring about cosmic rays or something else that depends on the meter system. So we have this whole disagreement on whether or not magnetic fields actually matter in terms of galaxy evolution. I would like to have an answer to that. I'd like to know I'm right, essentially. Because my PhD has very quickly become magnetic fields in galaxies, the PhD. So yeah, that 50, 60, 70 years from now, I would like to know that I'm right, essentially. Or I'd at least like to know either way.
So one of the big questions in my field, which is like, looking back so far in time, is we are now looking at a lot of objects that look very different from what we expect them to be. So we do something called a cosmological model, where we assume a bunch of parameters and we say, okay, based on this model, this assumption, this is what the universe is supposed to behave like. And with new and new telescopes, especially with JWST, to be honest, we have discovered this whole class of objects that we have absolutely no idea how they exist or why they exist. Because, simply put, based on this cosmological model, we expect galaxies to accumulate mass over a billion years, for example. It's not a billion years, but let's say for argument's sake. We are looking at galaxies that accumulated more mass than what, say, the Milky Way has in a span of 300 million years, which is ridiculous because we did not expect that much of matter to exist that far early in the universe. So what essentially is happening is, one, either our cosmological model is wrong and we are assuming wrong things, which is a really shaky ground to stand on because that's already going through a lot more problems. If you've heard anything about the Hubble tension, this is what it's talking about. There is conflicting information depending on what kind of objects you observe about how fast the universe is expanding, and this goes into how the universe is going to end, big crunch, blah blah blah. But these galaxies are challenging what we call galaxy evolution studies, like how quickly galaxies accumulate mass. And because we are looking at massive galaxies this far back in the universe, we think we will have to change some of the assumptions, if not all of them, in the cosmological model, and that's ruffling some feathers. I like drama, so I'm going to live for drama, and hopefully there will be drama in my lifetime. But yeah.
So I'll start off by saying that I'd be very lucky to make it 60 years in the field. Unfortunately, academia is a pyramid scheme, and as you go further up, there are fewer and fewer positions. And so I think to make it 60 years more in academia, I would be very, very lucky. But specifically in my field, so there's lots of different theories on the different mechanisms that affect star formation. So magnetic fields is one, which Thomas works a lot on. I don't really touch magnetic fields very much. But there's lots of feedback from stars that they think might affect how it interacts with clouds, sort of shocks to clouds, mainly supernovae feedback, and it'd be great to see how these actually affect, because we have great ideas of what we think is happening, but we're not really sure. It'd be great to see what's actually going on, and which things affect them more than others. So that'd be interesting to see.
Okay. Any final questions? Okay, in that case, I kind of building a little bit on, we talked about the very far future. What about, like, basically the next couple of years? So within the span of our PhDs, what are you excited about? What's happening right now that we should be really interested in?
So one of the things, the objects that I was discussing that are causing a lot of problems is called little red dots. If you pick up any science communication journal these days, this is the thing that comes up first, especially with GWST observations, because that's half of what I do for my PhD. And basically, these are galaxies from the very early universe that have black holes with masses comparable to the entire galaxy. So usually what happens is, you have a supermassive black hole in the middle of every galaxy, usually, holding things together, but the mass of this black hole is less than 0.1% of the total mass of the galaxy. These dots, these little red dots, as they read up because they appear red in the images, have a mass that's closer to 0.4% of the galaxy. That's like 40% of the total mass. And again, these are so far back in time, these black holes should not exist because we thought until now supermassive black holes form from mergers, but these are all isolated galaxies and they show no merger history whatsoever. So what happened was in the star that was that way, again, that goes back to the cosmological model, because under that assumption, we should not be forming stars that massive that quickly. So yeah, that's the next big thing. There's about 50 papers that are already out, there will probably be another 50 in the next year. Yeah, that's the next big thing in my field.
Well, I'm not sure about the next big thing in my field, but the next big thing for me specifically is I've been looking at a population study of the molecular clouds in the Milky Way, and there's an expected way in which you would think that the spin of the gas inside the clouds would go. And if they're not rotating, or well, rotating is a dangerous word to use, but if they're not rotating in that expected way, something must have caused them to rotate in a different way. And we can't say what that is, but that's the first steps into looking into the processes that are affecting star formation. Rule out what it's not.
Yeah, and then for me, there's this whole route. So I'm really excited time in simulations at the moment. We just had a simulation come out like 2 months ago called Colibri, means hummingbird, and there's another one coming out I think next year that's doing a similar thing, where we're finally getting more detail inside the galaxies. I got to talk about this last month, but up until now, big simulations of thousands of galaxies, they don't do particularly well inside the galaxies in terms of the structure of them, and there's been some advances in the last couple of years that are giving us so much more detail than we had before. So it's a really exciting time for that, and hopefully that will make all of our simulations more realistic. And finally giving that answer with ethicals. We'll see. But thank you for all of your questions. Thank you, Aparna, for chairman of the panel. We'll go on with the.
Just a quick one. If you guys have more questions, you can either tag us on the Instagram post or like DM us or something, or just leave it in question form behind the answer sheets from next time onwards. Like, we might make this a more regular thing if you guys are interested in hearing us nerd out about our subjects. So, yeah, that's about it. Thank you.